Swayam Prabha. Digital India. Educated India.
So, among the lot of heavyweight topics, we thought that let us give you some break and let us discuss some puzzles. The problem that I am going to discuss today started with a puzzle, but the problem becomes very famous for the proof that has been proposed for the problem. Okay. So, the problem that we will discuss today is it is known as art gallery problem, but you can think this problem as follows, that suppose you have a secure facility like an airport or a military base or maybe an art gallery where there are paintings in all over the world which are very expensive, and your objective is to place certain guards so that you can guard the whole arena that needs to be guarded. So, again when we see a problem, what we do? We try to model it as a mathematical problem. The closest to a art gallery or a airport or a military facility would be consider this to be of a simple polygon. So, we have a simple polygon and our objective is to I will place certain guards inside this polygon, so that every point of this polygon is being guarded. So, what do I mean by every point is guarded is that if I place the following guards, the red points are the guards. So, the guard here can see this point, this point, this points, this points, this points. It has a 360-degree angle of view, but none of the guards are able to see through the walls, which makes sense. For example, here the guard here is not able to see a point here because there is a wall blocking his view. Otherwise, it can see 360-degree points all around, 360-degree around himself, all the points. So, the question is, how many guards do you need to guard the whole polygon? Clear? What is the problem? Problem statement is clear. So, if you think of this problem, this is an algorithmic problem that given a polygon, I would like to find out how many guards are needed. But today we are not going to consider the algorithmic problem, but we will try to answer a combinatorial problem. So, before that, let me formally introduce what is a visibility means. In this picture, formally P and Q are mutually visible if the line segment PQ is inside the polygon P. Here P is the polygon in question. So, quickly let me know that can X see Y? Y sees Z? No, right? So, the definition of visibility is clear. Now, we would want to consider the following combinatorial question is that suppose if I give you a guard, if I give you a polygon with n vertices, you can find out that what is the minimum number of guards needed to guard that polygon. right. Suppose it is possible, and I denote the number of points needed to guard any polygon P is by G of P. There exists a number, whether I am able to compute or not, that is a different issue, but there exists a number that this is the minimum number of guards that needed to guard a polygon P. Now, let Gn be the maximum number of guards required to guard any polygon, or maximum taken over all values of Gp, where P is any polygon of size n. That means, you take any polygon of size n, there is a minimum number of guards needed to cover that polygon, right. I am taking the maximum of this value, that I am trying to asymptotically bound that you give me any polygon of size n, there exists a function f of n such that that many guards are always sufficient to guard any polygon of size n. Okay. Clear? Doubt? Okay. So, you would like to find that what is the asymptotic bound on this number. But there is a, I told you that this problem is famous because of the way it has been solved. But this problem was first proposed by Victor Klee to Shatal in a maths conference. This is a puzzle, and they have some time, they are roaming around, Victor Klee proposed this problem, and can you give a solution? And Shatal gave a solution, a complicated one, within few days. But then after the publication of the proof, Steve Fisk gave a very elegant proof, a very small elegant proof, and the paper is actually one page. The paper is actually just one page paper, and this is widely believed fact that this proof is from the book. So, what is the book? Do you know what is a book? Any math students? Okay, so to know about books, there is a famous mathematician called Paul Edos. He don't have any home, any properties or anything. His job is to roam around, like going from one country to other country and solving mathematical problems. He has positions in all over, say he has position in US, say Hungary, lot of places, and he used to travel and solve lot of problems. He always has lot of problems. He looks a maths Olympiad student, gives a problem, can you solve it? He looks a professor, he gives a problem. So, there are different kinds of subjects, and he has contributed a lot towards the development of the many domains in mathematics. So, he used to say that there is a book in which God keeps all the beautiful proofs, and sometimes he gives a chance to us the mortals to have a look at those beautiful proofs, and this proof is widely believed to be the proof, one of the proofs from the book. So, it is so beautiful in some sense. Okay. Enough of running around. So, this is a small history about this problem, but let us formally again define what is a, I have told you that we will model the art gallery or the secure facility as a simple polygon. So, what is a simple polygon? Is a closed polygonal curve without any self intersect. For example, the polygon in the left hand side, the green polygon is a simple polygon, whereas the right polygon with the right hand side is not a simple polygon. And we know that a polygon divides the whole plane into three parts: interior, exterior, simple polygon, that interior, exterior, and the boundary. And we will assume that all of these regions are connected. That means Whenever I say a simple polygon, I mean that a simple polygon without holes. This kind of polygons we will not consider. This is a polygon with hole. By simple polygon, I mean only a polygons of this kind. Okay, good. Enough of definitions. Let us do some brainstorming. What is G? G is, I am trying to find out what is the minimum number of guards required to guard any polygon of size n. So, please, if you understood the definition of G, please let me know what is the value of G3? 1, because what is a simple polygon with 3 vertices? Is a triangle. You take any triangle, you can always guard them with 1 vertex. Can we extend this? You take any convex polygon, how many guards needed to guard a convex polygon? 1, right? Even like something like this, 1 guard is always sufficient. What about G4? One or two? Okay. So, there are 2 cases for G4. One is all the 4 vertices are in the convex hull, that is it is a convex polygon, or there is 1 vertex which is inside the convex hull of the other 3. Both of these cases we can guard the polygon with 1 vertex. But G5, if it is a convex, 1. There are 2 other cases are shown in the figure. Think about this, why 1 is always sufficient for any polygon with 5 vertices. You can always guard any polygon of 5 vertices, simple polygon of 5 vertices with 1 guard. Now, can you let me know that, can we devise a function? What can be a function of Gn in terms of n? Can we say that sure? Let us go ahead. So, you think that Gn is less than equals to n, right? Okay, so let us claim a little bit more. Can we claim that if I see the whole boundary of a polygon, I will definitely see the every point in the interior? Right. Right? My question is, I will see the whole, so I am trying to like make the problem easier. If I am guarding the whole boundary, then am I guarding the whole polygon like the interior? Suppose this is my polygon and I have a guard here, here and here. Does these 3 guards cover all the boundary of the polygon? This is the all the boundary? No, which point is not covered? Boundary is covered, right? What about interior? So, not true. Are you still convinced that Jn is less than or equals to n? If I place a vertex, if I place a guard at every vertex, is it enough to cover the whole polygon? I I am just saying that because it works for this example does not mean that it works for every example. True, but if I place all the guards in all the vertices, it will work for here. But can we certainly say that it will work for any polygon? Simply I can say, only thing that I can say is that I do not know. I am not in a position to comment that this is certainly always possible. Convex polygon, one is enough, one guard is enough, that I know, right. This example also says that if I put guards in every alternating vertex, that may not be enough, right. So, this is the art gallery theorem, which says that you take any polygon of size n, you can always guard that polygon with n by 3 guards, and sometimes this n by 3 guard, there exist some polygons for which n by 3 guards are necessary. We need to place at least n by 3 guards to guard certain polygons of size n. Can you try to think of a example where of a polygon of n vertices for which we need at least n by 3 guards? Is the question clear or the theorem clear? If the theorem is not clear, we cannot propose a proof. It says that give me n by, give me any polygon of size n, I can always guard any simple polygon of size n with n by 3 guards, and there exist certain set of polygons for which I need n by 3 guards at least, or like floor of n by 3 guards. Can you come up with a example? Yeah, but a generalized which can be extended till like for any n. Hexagon, any convex polygon you can guard with one guard. So, this is the polygon, not difficult. If you think about 10-15 minutes, you will come up with this example. There are many other examples like this. In some sense, you need to select at least one of these 3. I am talking about vertex guard where you are only allowed to put guards in a polygon vertex. Then again you need one of them in these 3 vertices. You can make this width very small so that a guard here cannot see anything here or misses at least one point here. So, we have established the fact that there exist certain polygons for which I need n by 3, but is this bound tight? That is the moot question, that can we say that you give me any polygon, simple polygon of size n, I am always able to guard with n by 3 guards.
So, why specific n by 3?
Because I know that from this example I need at least n by 3 for certain polygons. So, I cannot do better than n by 3. Can we say that n by 5 is always enough to guard any polygon with n vertices? No, because for this example you cannot guard this polygon with n by 5, right. So, I know that I need at least n by 3, but the question is, does the lower bound matches the upper bound? That means I know that for some polygons I need n by 3, but it is necessary that all the polygon I can always guard with n by 3 guards. Clear? So, what is our objective? Our objective is someone will give me a polygon with n vertices, I have to find a guard set of n by 3 vertices so that it sees whole of the polygon. Okay. A quick definition: a diagonal of a polygon is a line segment joining 2 two vertices of the polygon such that the line segment is completely inside the polygon. For example, this is a diagonal, but this is not a diagonal, because if I join these two vertices by a line, the line segment is not completely inside the polygon. So, this is not a diagonal. This is a diagonal of a polygon. Okay. So, in the next you have already done a class on triangulation? No, right? Even maybe today or tomorrow you will do a class on triangulation. Triangulation says that you can always partition a polygon into triangles using diagonals. Why there exists such an, there is, you can always have the number of polygons, the number of triangles are always n minus 2. For any simple polygon using diagonals, you can triangulate any simple polygon using diagonals into n by 2 triangles. This we will learn in details in the today or tomorrow, but for the time being, assume that the claim I am making is true. Okay. If you believe that this claim is true, initially we claimed that, or initially I asked you a question that whether Gn is less than equals to n or not. Does n guards is always sufficient or not? Forget about n by 3. Can we say that n guard is always sufficient? Because every point in the polygon is part of some triangle in a triangulation. Now, if I place a guard at every vertex, it will be seen by one of them, right? Are you still with me? All good? So, can you give me a hint that why do I need to place guard at every vertex in a triangle? For a triangle, how many vertex we need to cover a triangle? One, right? If I have a triangle, how many guards we need to cover this? One is always, because it is a convex polygon. So, in other words, if I can devise a way to place exactly one guard at every triangle, that is sufficient. Are you with me? Suppose I say choose this one, this one, this one, something like this. One guard from every, I choose one vertex from every triangle and I place guards over there. Can I say that this will certainly cover the whole polygon? Because every triangle has a guard, and that guard will see every point in the triangle. If I choose any point in the polygon, it belongs to at least one triangle. And I know that every triangle has a guard, and that guard will see that point. Right? Right? How to claim that? What we are trying to, mathematically what we are trying to say. Okay. Keep true, but what I am saying is about the one guard in every triangle, right? Keep that question in mind, that how to choose one guard from each triangle. keep that question in mind. In between, let us consider a graph. What is the graph? Graph is the polygon with the triangulation. So, how we define a graph? A graph is nothing but a set of vertices and set of edges. What are the vertices? Polygon vertices. What are the edges? Either polygon edges or the edges from the triangulation. This is a planar graph. It is a graph, more than it that it is a planar graph, right. What are the properties of planar graph? We know that it is, from basic graph theory, we know that it is a 4 colorable. Any planar graph is 4 colorable, right? Everyone knows that. But this is a very special kind of a planar graph, and suppose we can show that any such planar graph which is a diagonals and the polygon or a triangulation with the polygon is 3 colorable. Suppose we can prove that. Then what? Suppose that I am claiming that this graph here in the picture is 3 colorable. Can we say something? Think. What we are trying to say?
Using only one color, we can place guard. Suppose we use only one color and place guard, or place a guard at only those vertices. So we get.
Very good. Very good. What he is suggesting is that suppose this graph is 3 colorable. Suppose, I don't know, I don't have a proof yet. Suppose this graph is 3 colorable, then what I know that every triangle gets exactly 3 colors, because that is a clique. And among those all these 3 colors, I can choose the color which is least used. There exists a color which I have used at most n by 3 times from pigeonhole principle, right. What I will do? I will select that color. Here in this example, the color, that least used color is blue. I will place guards at that color, and then we will have one guard at each triangle, exactly one guard at each triangle, and that will prove that any polygon can be guarded with n by 3 colors. But we need to show that this graph is 3 colorable. Till now, are you with me? It's easy, it's a very beautiful argument. Right? That we all learn how to color graph with, in a basic graph theory course, and how to color a graph with 5 colors. We know that every planar graph is 4 colorable. But this is a very cute example or a very cute application of graph coloring. Are you with me? If it is not clear, please raise your hands. So, I will go through the proof once again. We are not complete yet. With some assumption, we have proved that, with the assumption that any such graph can be colored with 3 colors, we have proved that n by 3 guards are sufficient.
He comes from that converting now that 3 colors are used to color the.
You can color this graph with 3 colors.
So from there the n by 3 go. From there then I get.
Yes. Okay. question, why this graph is 3 colorable? Hmm? Hmm? No, that's a hunch, that's not a proof. Let's see why this is 3 colorable. You have learned what is a dual of a planar subdivision. What is the dual of this triangulation? Is a each triangle is a vertex, and we are joined 2 vertices by an edge if there is a edge shared between 2 triangles. So, for this triangulation we have the following dual graph. Can we say something about this dual graph? Tree? Very good. So, if I merge both these claims, this is a tree with degree 3. This is your claim. You are actually now proving the theorem. Okay. Why this is a tree? What is the formal argument? What is a diagonal? Because this is a simple polygon. If I cut along the diagonal, I will get 2 separate polygons, because this is a simple polygon without holes. Right? If I cut along any diagonal, say this one, and take the closure of both of them, so I will get 2 polygons. What is the diagonal represents in a dual graph? An edge of the dual graph, right? So, when I cut along the diagonal, it divides into 2 parts. What did that transforms to the dual graph? That if I remove any edge, it will become 2 disjoint subsets. Any edge, removal of any edge leads to 2 disjoint subsets. What is the graph that has this property? Right? So, this is tree. So, the dual is a tree. So, what? So, dual graph of a triangulation is a tree. Oh, yes, that is true, but how that will prove that this is a 3 colorable?
We can, for if this is maximum degree 3, then we can, for any point on its neighbor edges are 3 maximum.
Yes.
So we can color it with one color and neighbor edges with another.
No, it may not be. So, I am not trying to color the vertices of the tree. What is the chromatic number for a tree? So, it is not even 3, it is less than 3, it is true 2. But are we trying to color the dual graph? We are trying to color the polygon with the triangulation, or we are trying to color the vertices of the polygon. So, what we will do is, we will prove by induction. Yes. Let us see, to give you a cute proof. Why? Because, let me go through the proof, then you will understand. Suppose I want to prove that any graph or any triangulation on any polygon with its triangulation with n vertices is 3 colorable. I want to prove this by induction. That means I am assuming that this statement holds for any value less than n. and I have to prove for n. What is the base case? I have a polygon with 3 vertices, I can color it with 3 colors. So I am trying to prove that any polygon with n vertices can be colored with 3 colors by induction. I am assuming from the induction hypothesis that this is true for any polygon with less than n vertices. So, this is my polygon with n vertices. What I have to do? I have to remove something. Edges. I have to reduce the size of the polygon. But how I will join the colors? You are right, you are almost right. There is a simple case that what he is suggesting is that I will remove any edge, I will get 2 polygons of lesser size, apply induction, but how I will merge these 2 colors? Because in one side it might get red and blue, in the other side is blue and green. How I will merge them? You see my point? Suppose I remove this and I find the coloring of this side and find the coloring of the other side. In this side S1, this is S2, S1 colors this with red and green, and the S2 side we are colored with green and blue. That will conflict. When I merge, that will conflict. Now we will see that from where the idea of the dual graph comes. Right? What we know? The dual of this graph is a dual of a triangulation is a tree, and any tree necessarily have a leaf node. What I will do? I will remove that leaf node. What do I mean by removing the leaf node? What is a leaf node? It will be a triangle, right? It will be a triangle which has only one neighbor. That means if I remove this vertex, this edge will remove, I will remain with a polygon of size n minus 1. 1. I have removed only one vertex, right? Right? This is a leaf node and it has only one neighbor. Now from induction hypothesis what I know? I can color this polygon, the new polygon, with 3 colors. What is my induction hypothesis? That any polygon with n vertices can be colored with 3 colors, and I am assuming that for any value less than n, this is true. So we have generated a polygon with vertices n minus 1. So from induction hypothesis, I know that this holds for this polygon. So color them. Now how to color? Now bring the triangle back, and how to color the last vertex? Right? In this coloring I have colored its 2 vertices and I have used 2 colors. I still left with 1 color. I will color the other vertex with that color, and this is, as this is a leaf node, it do not have any other neighbors.
The claim that he was making, like we separate the polygon into 2 polygons, and then you said that suppose like in the lower polygon we had red and blue, and in the upper we had green and red. So can't we recolor the upper polygon such that
No,
green becomes red?
no, because we cannot impose anything. That is the beauty of the or restriction of the induction hypothesis. You cannot impose anything on the coloring that returned by the smaller problem.
But like we can change reds to greens, greens to blue.
But we need a formal proof that you can always do that.
But that's very trivial, right? We can always.
And you can always come up with such thing that you need to prove. Doesn't, it needs a proof. But anyway, you can think, you can write down a proof and let me know. Okay? So this is the final theorem.
I didn't still able to understand why. So that proof describes how to color this graph in using three colors.
Hmm.
But where is the connection between that and the duality? And
Okay, and how I have, because I have claimed that there exists a leaf node.
no, that is not the leaf node.
Yes, this is a leaf node in the dual graph.
No, you did not use that one, that original graph. That one you.
So in the previous example, where?
No, next one. Just to prove of three color.
Yes, this is the proof of the three color.
So there, so that is not the leaf node.
Which one? This is not a, this is a leaf node.
No, that is the leaf node, but that one, that triangle, the leaf node is inside a triangle.
Yes, no. What I am saying is the leaf node is in the dual graph. I am not said that there will be a leaf node in the triangulation. There will no leaf node in the triangulation.
Okay.
Because triangulation is not a tree.
Yes.
Right? But the leaf node will be in the tree.
Leaf node will be in the tree.
Right? And what is the object associated with each vertex of the dual? It's a triangle.
Triangle. Yes.
Right? That means this triangle will share a edge with only one other triangle. Right? That means if I can color the rest of the graphs, this will get some, these vertices will get some colors in the triangle, in the coloring of the n-1 sized polygon. And as this triangle is not neighbor of any other triangle, my claim is that I can extend that coloring to create a coloring for our original triangulation.
Still I don't understand why using dual graph.
Hmm?
I can color it. So without using this dual graph, can't I color it? Can't I prove using three colors?
Of course, there are plenty of ways to prove the same theorem.
Yeah, but why that idea that the duality, dual graph idea is coming? Still I'm not able to connect it.
Yes, but is it wrong?
Not wrong.
It comes as a surprise, but it's not wrong. Mathematically,
What was the need of making that dual graph? Because just to get a leaf node.
because I want to create a polygon of lesser size. That is the need. Because how can I use induction? If I am trying to prove,
Induction part is clear. That is the graph is three colorable. That is clear. That is understood.
Even though if we said that, sir, the triangle, leaf node triangle, the leaf nodes triangle, you are saying that it will share the edge with only one triangle. So what it's
how can you prove that there always exists a triangle which shares a edge with only one other triangle?
So instead of taking the leaf node, if I take any internal node, will it work?
No, that's what. It might work, but I need a separate proof for that. I am not saying this is the only proof.
So what could you take that leaf node, that the triangle associated with the leaf node? I can take any node, any triangle.
So I will take this triangle, right?
Yes.
Right? Suppose I take this triangle. What is the degree of this triangle? Like 3. how many parts we have? We have 3, right? So, we have 2 parts. This is one part and this is the other part, and I cannot impose any restriction on what kind of coloring I will get. So, suppose in the coloring of the by the induction hypothesis, this is red, this is green. This is a separate coloring, right? This is part 1, this is part 2. Here I get a coloring of red and green. In this part I get a red and green, both are sound coloring, but if I merge these 2 colors, did I get a proper coloring of the original polygon? No, because in this the triangle this and this gets a same color, this edge gets the same color.
Only green color has to be there, otherwise it cannot merge it.
Huh? Now, in the by the induction hypothesis, I will get some proper coloring of this graph. In the induction, this is a proper coloring of P2, this is a proper coloring of P1, but if I merge them, I am not getting a proper coloring of.
No, then weak induction is only applicable. In strong induction it cannot be proved.
Right? I am not saying this is the only way to prove. This is one way to prove. You don't have to necessarily use induction. That's the beauty of mathematics, right? Certainly came up with another proof of this theorem. This is one way to prove this.
Okay, so we concluded that the graph is 3 colorable.
Yes.
Right?
Yes.
Then from there the idea that n by 3 how it came.
Okay. Why now your question is why the graph is 3 colorable, then why it is n by 3. So let me go back to
That is independent set you are asking. That largest n by 3.
look at the color classes. Each vertex gets a color. That means there exists a set of vertex. There is this color class. That means set of vertices that color gets a same color will have size n by 3. Right? So there are n vertices you are putting into 3 boxes, like 3 colors. One bag will have n by at most n by 3, and at most n by 3 vertices. I will place a guard at all those vertices. For example, here the least used color is blue. You can verify that. And what I will do is I will put a guard on all the blue vertices. Now, every triangle has a blue vertex. Now I have to prove that every point in the polygon is guarded by at least one point. Every point in the polygon is part of our triangle.
That is the reason you are using this.
Clear? Doubts?
So the statement he asked was, how can we be sure that corresponding to a leaf node, the triangle associated with a leaf node, it can at most have only one triangle
What is the definition of a leaf node?
I mean, that is why that's what I understand. That is why we needed a leaf node.
Yes.
Not that we couldn't have.
Leaf node is a degree 1 vertex. That means if you have a tree, so this is a leaf node, this is a leaf node, this is a leaf node, this is a leaf node. So it is only one neighbor by definition of a leaf node. You can show that every tree has to have at least one leaf node. Every tree with size at least 2. Clear? Okay. That's all. Thank you.
So the graphs which are not 3 colorable, they may come across such a problem. How to solve triangulation is not possible.
Triangulation is possible.
Suppose there is a
So
geometrical figure where
So the
triangulation
beauty about coloring that we don't understand is that this color classes gives a set of independent sets. Now you can argue on them. Suppose you need the independence property, suppose the graph is 10 colorable, that means you can partition into 10 independent sets. Yeah. Now depending on the application, you how to use that, you have to decide that.
So this is for so n by 3 colors is the colors required to property only for this triangulation. It will not work for the identity.
No, 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 it's not a general statement or anything. It works for this argument. That's it.